Bienvenidos, kids. Today we're going to learn about our last topic for Unit 4 before our exam, which is this next Friday. And today's video, 4.3, is about projectiles. That's when we throw an object. There's three types of projectiles that we've looked at before briefly when we were talking about gravity. There's the projectile where you're just dropping something. Okay, you're not pushing it with any kind of force. You're literally just dropping it. The second type is when you throw something just straight up into the air. Eventually, it reaches a point at which it stops moving for like a split second, and then it falls back downward. So it slows as it falls up, as being thrown up, and then it speeds up as it's being thrown downward. So the third type, which we're going to look at a lot today, is when the object is thrown upward and at an angle. So it's not thrown exactly upward, it's being thrown with some sort of angle, and it's going to show this parabolic shape, which is something you see with any kind of projectile, is with this parabolic type shape. So a projectile, really the definition of a projectile is any kind of object in which the only force acting on it is gravity. So we would be looking like these three projectiles are projectiles after they leave the person's hand, because after they leave the person's hand, there's no longer a force being acted on them. So the free body diagram of every projectile looks like this. So let's look at some just diagrams here to get an idea conceptually what's happening in a projectile. So in this first picture, there's a cannonball, and it's being exploded from the cannon, and it's going in a straight path. That's called the gravity-free path. So this is if gravity does not play a role, the speed of the object, the velocity of the object in the horizontal direction doesn't change. Do you see that? It continues going with the same speed that it was left in. So if this was left, if it was shot at a speed of 5 meters per second, then at the end, right here, it's still moving with a speed of 5 meters per second. Why is that? Well, remember that if there's not a force acting on an object, it's not going to change whatever it's doing, right? That's Newton's law of motion, is that an object at rest or an object in motion, like this object, will stay in motion unless it's acted on. So there's no force acting on it, so the speed is the same. What happens when a force starts acting on it? So here's what happens in real life. Gravity pulls the object down, right? Force is going in the downward direction due to gravity. So it's pulling the object down. So actually there's a speed downward now to this cannonball. The speed is increasing downward, vertically. So the speed vertically is increasing, okay, due to gravity's acceleration. The speed vertically, this direction, is still going the same because there is no force acting on the speed in the left or rightward direction. There's no acceleration in the left or rightward direction. So the forward speed is the same. The downward speed is increasing due to gravity. Let's look at a projectile that's being thrown not horizontally, but vertically. So it's being thrown up into the air. Without gravity, the speed is going this direction constantly. Remember, if we took this speed and we broke it into its components, this is the vertical speed here, and then this is the horizontal speed here. Okay? Both of them are staying constant because there's no force. Now that there's a force on it, okay, here's your object. It's got a vertical speed. It's got a horizontal speed. The horizontal speed does not have a force acting on it. There's no left or rightward force. So the vertical speed keeps going at the same speed. Do you see that? So if we're looking vertically here, the ball is in the same space along the x-axis at every point because it's staying the same speed. It's not slowing down. But the speed vertically is being changed, okay? So it used to be going up, but what's happening now? Now the speed's going down, down, and greater and greater and greater. So my downward speed, or my vertical speed here, is being affected because there's a vertical force. Okay. Let's look at this with some numbers. Okay, here's the cannonball that's being shot vertically. There's no horizontal up and down speed. It's only being thrown this way. So the speed horizontally, I labeled it as VH. They're labeling it as VX because it's on the x-axis. So here's your speed. Notice what's happening to your horizontal speed here. Is it changing? No, it's not. Why is the speed not changing in this direction? Why is speed or velocity constant in this direction? Well, remember Newton's law, speed will be constant unless a force acts on it. Is there a force acting in the left and right direction on the cannonball? No, there isn't. After it leaves the cannon, there's no force going left or right, so it's going to stay the same speed. Now, what about the speed downward? The speed downward is increasing. It's accelerating. Why is the speed downward? Why is velocity downward accelerating? Well, you should say because there's a force downward. There's an acceleration force downward. Force due to gravity of this object. We don't know the mass of the object, so we don't actually know the force, but we do know the acceleration, right? The acceleration of the object downward is negative 9.8 meters per second squared. So see how the vertical velocity here, that's the Vy, it's increasing by 9.8 meters every single second. But the horizontal velocity is constant because there's no horizontal force. Okay. Same thing's happening here. If it's being shot upward, do you see how the vertical force here, the force going to the right, doesn't change? Okay, so our value is not changing. I circled the wrong ones here. Whoopsies. This force is the vertical force. So all the ones I just circled, those are the vertical forces. They're not changing. I mean, the horizontal force. The horizontal speed is not changing because there's no horizontal force. The vertical speed here is changing because there's a vertical force. So you can see here the vertical force is changing because there is a vertical force. So these are the conceptual things you need to know from this first part of the video. The projectile is any object where the only force is gravity. So you should know the free body diagram of any projectile ever just looks like this. One arrow down, label it F of G. Okay, projectiles travel with a parabolic trajectory. Parabolic means it looks like this. There are no horizontal forces acting on projectile, so there's no horizontal acceleration, which means this direction, velocity is constant because there's no horizontal force. Okay, the horizontal velocity of a projectile is constant. So your initial speed in the horizontal direction will equal your final speed in the horizontal direction because there's no change. It's constant. Now vertically up is up and down. The vertical speed accelerates because of a vertical force, gravity, and it accelerates by a value of 9.8 meters per second in the downward direction. The last thing you need to know is that the motion horizontally is independent of the motion vertically. And what that means is it's just talking about distance. So if here's your object, okay, you're on a cliff and you throw it, the distance this direction, okay, the distance horizontally is different and separate than the distance vertically. We're going to look at that in a little bit. Okay, so that's kind of conceptually what's happening with a projectile. Now I want to talk about mathematically how we can use these two formulas to solve projectile problems. This first formula is really when you have VF, your final velocity, VI, your initial velocity, time, and acceleration. So if you have these four, or if you're solving for one of them, you'll use this formula, okay? this next formula includes distance, but it doesn't have final velocity. So it's got initial velocity, time, acceleration, but instead of final velocity, it has distance. So we're going to be looking at these two formulas and how they come to play. So horizontally and vertically, we have to look at the motion in two separate ways, because if here's your object, okay, it's going to have a velocity this direction. This is the horizontal velocity, the x velocity, and it's going to have some sort of speed in the vertical direction. So there's going to be a velocity that's in the vertical direction, or Vy. Okay, so this is our Vy, and then this is our Vx. Now, let's look at Vx. If it's being thrown in this direction, what do we know about horizontal speed? Horizontal speed is constant. It doesn't change in a projectile because there's no force horizontally. So what does that mean about Vf and Vi? It's the same exact amount, right? Vf and Vi will be the same because your speed is constant. It won't change. If speed is constant, if speed doesn't change, what does that mean about acceleration? If your speed's not changing, what's your acceleration? You should say it's 0. So if this formula, acceleration is 0, these two numbers equal each other, this formula is not helpful at all because 0 times t will give me 0. This is a value. If I subtract Vi from both sides, guess what? That's also going to give me 0. So this formula is not helpful at all to use when you're looking at speed horizontally. Now let's look at this formula. How does acceleration being 0 affect this formula? Well, let's say we take A right here and I replace it with, oops, that was a T, with 0. What does that do to this entire part of the equation? It all becomes 0 on this part of the equation because they're all being multiplied. So really, the only formula that's useful for horizontal motion is distance equals initial velocity times time. This part of the equation you won't be using, and this equation you won't be using. So this is really the only equation useful when we're looking at the speed of a horizontal motion. What about vertical motion? What do we know about vertical motion? We know in vertical motion that it will always be accelerating due to gravity, so the acceleration is always going to be 9.8 meters per second squared. Okay. Couple other things. If your object is being thrown upward and landing down in the same spot. Okay, so if it's being thrown at an angle and it's landing at the same spot, your initial velocity will equal your final velocity. Okay. That's if you're being thrown at the same spot, like this. If you're being thrown atop something and being thrown downward like that, your final velocity, you're not going to be sure what that is, but your initial velocity in this direction will always be 0. Okay, because see how if it's being thrown here, its first speed is in the leftward direction. There's no speed up or down yet. Okay, gravity doesn't play on it immediately. So if it's being thrown downward, your initial velocity will always be 0. If it's being thrown upward and falling back down at the same spot, your initial speed and your final speed will be the same. Okay. Couple other things about if it's being thrown upward. If it's being thrown upward, you need to know this term, peak of trajectory. Trajectory is just the path that the object follows. That's all trajectory means. Peak of the trajectory means the highest point of the trajectory, which is right here. At the peak of the trajectory, there's some important things to know. When you're at the top right here, the time it takes to get to the top is the exact same amount of the time it takes to get to the bottom. So time to get to the peak is actually twice the total time. Think about it. If it takes me 2 seconds to throw the ball up to the top, it'll take 2 seconds to throw the ball back down. The total time is 4 seconds. So my peak time is half of my total time. Oops, I said twice. I didn't mean that. I meant half. Sorry. It's half my total time. Okay. Also, the distance vertically, if you're throwing it upward, and you want to know the distance it takes to get to the top here, you want to keep in mind that if you're using this formula right here to solve for distance, it's going to give you the distance from your whole trajectory. So what's the distance vertically after I throw it up and it falls back down? The distance is 0, right? If it starts here at 0 meters and I throw it up and then it falls back down to 0 meters, what's the distance? 0. So when you're using this formula to find the height of your trajectory, you want to use not the total time, because the total time will give you your full throw. You want to use the half time. If you want to find the distance here, you need to use the time it takes to get to that point. And we'll do a sample problem with that. Okay, so looking at these formulas, we're going to solve this first problem. Okay, a pool ball leaves a 60-meter high table with an initial horizontal velocity of 2.4 meters per second. The first thing you do whenever you're solving these problems is to make a table. So here's a table, an example table of how I want you to draw on all of your problems. You need to write down the horizontal factors, so the initial speed horizontally, the initial speed vertically, the initial speed horizontally and the final speed horizontally, the distance horizontally and the acceleration horizontally. Remember, horizontal is this direction, so draw, whoops, that's a bad arrow. Draw an arrow to help you remember that, and then vertically is up and down, okay? So horizontally, and let's just go ahead and draw the picture here. Here's the 60-meter high table. Here's the ball. It's not 60, it's 0.60. And it's being thrown this direction with the speed, and we know it's going to fall down like this. So we're dealing with a ball that's being thrown horizontally. It's not going up and back down, okay? So what do we know about horizontally? We know it has an initial speed of 2.4 meters per second, so let's write that out. The final speed, we do know. Horizontally, so the speed horizontally at the very end. Okay, this is the initial. Here's the final. Will the speed horizontally be any different than it was at the beginning? No, it's going to be the same. How do we know that? There's no horizontal force, so speed will be constant. Okay. Vertically, at the beginning, there is no vertical speed because it's being thrown above something. There's no downward or upward speed. Okay, we're not throwing it upward at all. We're not throwing it downward at all. We're throwing it straight. So since we're throwing it straight, it doesn't have any vertical speed. Okay. There will be a speed vertically at the end because gravity is changing the vertical speed. We don't know what it is yet. Distance vertically is referring to, okay, it's right here at the beginning. How far did it fall vertically? Okay. The distance horizontally is referring to how far did it go along the x-axis. Okay. And let's talk about acceleration. There is no acceleration horizontally because the speed's not changing. So it'll always be 0. The vertical speed will always be negative 9.8 because it's accelerating due to gravity. Okay. So this is everything we know. Oh, we also know that the table is 0.60 meters high. So we know this. Okay, so that's the vertical distance. 0.60 meters high. I'm going to put negative because the ball is falling that distance. It's not going up that distance, okay? So we have all this information. So now we need to look at our formulas. Well, what are we trying to look for? We're trying to find the time. I put time here in the middle because horizontal time and vertical time will be the same. Always. So we're looking for time. And we want to find the horizontal distance. So we want this right here. We want the green arrow. We want the distance. So we're looking for distance and time. So go ahead and star the things you need. And let's see how we can find them. How can we find the distance horizontally? Well, this is the only formula we use horizontally. We need distance. We have our initial, right? That's great. But we don't have time. So since we don't have time, can we find time using vertical formulas? Well, both of these have time in them. Let's see which one we can use. We have distance, we have our initial speed, and we have acceleration. So we could use this formula. Why can we not use the top formula? Well, we don't have the final speed, so we can't use the top formula. So first, let's use this formula. To find distance. So I'm going to put in, oh, well, we're not finding distance, we're finding time. Here's the distance. My initial speed is 0, so 0 times time is just 0, plus half of my acceleration, which is negative 9.8, times t squared. So I want to get t by itself. So in order to get t by itself, I need to move this to the other side. The 0 we can just kind of take out. So let's divide both sides by half of negative 9.8. So now we just get t squared. So how do you get rid of the t squared? Well, we need to put a radical around everything. But let's go and get a number here. So I get 0.122 is t squared. Now I can put a radical to get rid of my t squared. So it's t equals 0.35 seconds. So that's time. It takes 0.35 seconds for this ball that's dropped off the table to hit the ground. Okay. So what next? Well, we want to find distance. So we can use this formula right up here to find distance. We're looking for distance. What's the initial velocity? It's 2.4. And the time we just found was 0.35. So when I multiply them together, my distance is 0.84 meters. Now, it's important to keep in mind that when you're doing these formulas, you need to remember which set of data you're looking at. Are you looking vertically or are you looking horizontally? Because the numbers cannot be shared. The only number you can share is time. Okay. Let's look at another problem. This one's a little bit more complicated. Okay, so this example, it says, a football is kicked with an initial velocity of 25 meters per second and an angle of 45 degrees. So this example is not this one right here, where it's being thrown off. It is this example, okay? Right here, we're being thrown upward and we're coming back downward. Problem with this type of picture is that we don't know the horizontal and the vertical initial speeds. Here's your object. We don't know vertically what it was thrown with and horizontally what it was thrown with. Okay, this is vertically is your y and then horizontally is your x. We don't know these. We do know the resultant speed. It says it was kicked with an initial velocity of 25 meters per second and the angle was 45 degrees. If we rearrange this to look like a triangle, this side is 25. This one down here is your adjacent. Adjacent is your horizontal speed. Opposite is your vertical speed. The angle is 45. How can we find opposite and adjacent if we're given the resultant and the angle? Well, we can use these formulas to find our opposite and adjacent sides. So here I plug in sine, my angle is 45. I'm going to move h to the other side, which is 25. So this will give me my opposite. When I do the calculations, my opposite is 17.7 meters per second. What does that stand for? Well, opposite is it's my upward speed, my vertical speed. So my initial vertical speed was 17.7 meters per second. Okay. Okay, what about my adjacent? Well, I'm going to rearrange. So I put my hypotenuse on this side, so it's looks like this, times my angle, equals A. So A actually comes out to be the same number. It's 17.7. So what does that stand for? A stands for my horizontal initial speed. So this is the initial speed of both of my objects. Now remember, what are some of the things we know? We know that horizontally, there's no force. So the speed is the same at the beginning and the end, and there's no acceleration. We always know that. Okay, vertically. Well, vertically, it's a little different than it being thrown off of thrown straight forward. Right now, we're being thrown upward. So we have a vertical speed going upward as it's falling, and then it's going to fall back down to the same spot. So it's going to have speed going up this way, and then the speed's going to be increasing downward. So there is a peak to this trajectory, right? There's a peak. There's a midpoint. It's going to be kicked from the ground, and then it's going to fall back down and hit the ground. So it's starting and finishing at the same spot, which means that their speed is the same, the beginning and the end. It's just a negative coming down. That's something we learned earlier. Okay. Acceleration is always negative 9.8 meters per second squared. So we know everything except for distance and time. It wants to know the time of the whole flight. It wants to know this. It wants to know the horizontal displacement, this, and the peak height of the football. Okay, don't worry about peak stuff yet. Let's just do the first two things. So what formulas can we use? Well, we can't use, remember that the formulas on the left are my horizontal formula, and that these are my vertical formulas. So my horizontal formula, D equals VI times T. I don't have T or D, so I cannot use this formula. So let's come over here on the right. We can use this formula to find distance, except we don't have time. So if we don't have distance, we don't have time, we can't use this formula. So we're going to use this one right here. VF equals VI times AT. VF equals VI plus A times T. We have VF, we have VI, we have A, so we can find T. Let's do that. The final is negative 17.7. Our initial is 17.7. A is negative 9.8, and we're looking for T. Let's move 17.7 to the other side. And when I do that, I get negative 35.4. And then let's divide by negative 9.8 to get T. When I do that, I get 3.61 seconds. So that's my time. Okay, so now I have time. I can solve for distance here because they wanted the horizontal distance. So my horizontal distance formula, if you remember, is D equals VI times T. So I'm going to put it over here. D equals VI times T. So the distance we're looking for, our initial was 17.7 right here. Our time, which we can share, is 3.61. And so my distance comes out to be 63.9 meters. So we have both of the things they asked for. Now they did ask for a third one, the peak height of the football. So the peak height of the football is it's the distance vertically. I mean, height is vertical. So we need to use a vertical formula. We need to use this vertical formula because it has D in it. So let me write it out down here. D equals VI times T. I think it's times T. Yep. Plus half of A times T squared. So the D here we're looking for is the distance here. Here's the football, it's kicked, that's the peak, and then it falls down. So we're looking for, everything we're looking for is the half. Okay, so we're looking at really this section here. What's the distance there? So the initial speed is still the same as my initial speed that I listed. It's 17.7. The time, however, is not the full time to do it. It's half the time because we want to look at the peak. So I'm going to put the time, which was 3.61, and I want to do half of that. Oh, I just put A here. I need to change that A to my actual acceleration. What's the acceleration vertically? It's negative 9.8. When I do that long, complicated math, I'll get 15.9 meters. A way to remember to divide it by 2 if you're looking for peak height is if you don't divide it by 2, can you guess what distance you're going to get? 0. Because what's the height difference between the start of the kick and the end of the kick? There's no height difference, right? It's 0. So if you end up with 0, you know you did something wrong. So we want to look at, okay, halfway through the kick, what's the distance height-wise? And then that will get us the answer we want. Okay, I have gone over the 2 types of problems that to solve. One is when it's kicked upward and it falls back down at the same spot. And the second one is if it's kicked just straight out and it falls downward, like off a cliff or off a table. You have one practice problem to do, and you need to decide which type of way you need to solve it. Do you need to solve it like it's going up and back down, or is it just going straight and down? Because that determines a little bit of how we solve the problem. And that's it for today. I hope you guys have a great day.